Thank you for coming to lecture 38, which is an optional. So that means you do care or you are learning in this class. Glad to hear so. Let's go back to the energy balance derived for a single species entering and leaving the system. We said if we want to write an energy balance for the case where we have multiple species entering and leaving the system, simply we add the summation here, right? And we said then the energy coming in, the energy of the stream coming in is simply calculated from summing up the energy of the constituents. So we simply took Fi times Ei and sum it over all the species coming in. Upon some simplification, we said we neglect the kinetic energy and the potential energy coming in, so we only concentrated on the enthalpies. And of course now we have the shaft work here because the flow work is part of this term now. Okay, and then we did some other simplifications and we rewrote the equation this way for a steady state. طيب. The question now is, are the last three equations applicable to all kinds of solutions, meaning ideal and non-ideal solutions? In other words, I'm saying, if I want to evaluate the total energy rate coming into the system, the total energy rate coming into the system, can I use this summation? Or if you look at this equation, as if I'm asking, if I want the total enthalpy rate of the stream coming in, can I evaluate it through the summation of the molar flow rate of the involved species times their respective specific enthalpies of these species coming in? طيب, if you want more simplification, I would say, as if I'm saying for this stream which is coming in, if I want to calculate the volumetric flow rate, can I simply calculate it? So it is naught, okay, epsilon naught, and of course we don't use T, but let me just write it there, okay. Can I really calculate it from using the molar flow rate of the species coming in times the specific volume of each species? Okay, and of course I'm not talking about the units. I know the units are correct because in this case I have mole per second times cubic meter per mole, so the units are correct. I will end up with cubic meter per second, which is the volumetric flow rate. I'm talking about this equation which I'm using. Is it correct to calculate the total volumetric flow rate that is entering through just summing up over this product, which is the molar flow rate of the entering species, times its specific volume? Of course, the specific volume is coming from the specific volume of the pure species. So is this correct? The answer is no. In fact, what we're doing here is when we use this, in fact, we are neglecting any enthalpy changes resulting from mixing. We simply assumed that the partial molar enthalpies are equal to the molar enthalpies of the pure component. So that's what we assumed. And of course, this is not true for all the solutions, correct? Because if you have non-ideal solution, then we have enthalpy of mixing. In other words, in that case, the partial molar enthalpies do not equal the pure component specific enthalpies. Okay, to clarify it more, again, epsilon, okay, if you have an ideal solution, epsilon simply can be calculated from summation of Fi Vi, which could be if the solution consists of two species A and B. So it is the molar flow rate of A times the specific volume of A plus molar flow rate of B times specific volume of B. And how do you calculate the total enthalpy of a stream? Well, simply summation of Fi times Hi, which if you have two species is Fa times Ha plus Fb times Hb. That if the solution was ideal solution. However, in reality, not all solutions are ideal. Okay, in reality, if you have a non-ideal solution, then if you want to calculate the total volumetric flow rate, so you should use the summation of molar flow rate times the partial molar volumes. So that would be Fa times Va, you call it Va dash, okay, plus Fb times Vb dash, where Fa dash or Vb dash are the partial molar volumes, which you have learned about in thermodynamics too. Remember the partial molar properties, okay? And the same thing with the total enthalpy of the stream coming in or leaving out should be calculated from the summation of Fi times Hi dash. Okay, that is the partial molar enthalpies. Do you see the difference, Shabab? Do you see the difference? So if it's an ideal solution, it's simple. Just calculate the total property by multiplying the molar flow rate times the properties of the pure species. However, if it's not an ideal solution, then you cannot use the pure species properties, the pure species enthalpies. You have to use the partial molar property or the partial molar enthalpy in this case. Tamam? Okay, let's remind you more about thermodynamics. Right. Let's prepare 2 moles of a 30.75 mole percent methanol aqueous solution. So you have methanol and water. Measure the liquid's volume and temperature before and after mixing. Okay, so let's do that. So the aim is to prepare 2 moles of 30.75 mole percent methanol aqueous solution. Okay, let's go to the molar mass of these two species, involved species, the methanol and water. We have them. Tamam. The densities at 25 degrees C, we have them as well. The molar volumes, which is ml per mole. What's the volume of the pure species, methanol and water, per mole? How do you find it? Of course, you can find it from the density and the molar mass. Okay, so these are the values. Then we have the mole fraction. For mole, it's for methanol, it is 30.75, so we have it there, and for water is the rest. And the number of moles, you can multiply this by 2 to give you the number of moles in the solution. Right. So we know now how many moles we need from methanol and how many moles we need from water, correct? Okay, that means if you multiply it by the molar volume, multiplied by the molar volume, you can tell how many ml you should have from each species. Okay, so let's calculate the methanol and water volumes that need to be mixed to get the desired composition, and then determine the solution volume, assuming ideal solution. Okay, so we said we can calculate the needed volume of each species by multiplying the number of moles by the molar volume. Tamam. Okay, and the same thing we do for water. So now we know that we have to get this much ml, tamam, from methanol and this much ml from water, and let's mix it. And of course we can calculate the solution volume if it would form an ideal solution. Simply we would say 25 plus 25 equals 50. However, we know from our experience that methanol and water do not form ideal solutions. Why is that? Because methanol and water really have good affinity to each other. Methanol and water molecules get attracted to each other through van der Waals bonding or through the hydrogen bonding because of the partial polarities of water and methanol. طيب. So now let's calculate it experimentally. Let's calculate the solution volume experimentally. Yalla, let's mix 25 ml of methanol with 25 ml of water, and experimentally we find that it is 48 ml. 48 ml, it's not 50 ml, it's 48 ml. Why it is less? Why is it less? Well, it's less because we said that the bonding between methanol molecules and water molecules are actually stronger than the bonding between water and water molecules or methanol molecules. So when we mix them, actually, when we mix them together, they attract, the molecules attract to each other due to the polarity of these molecules attract to each other, and the volume shrinks, and then we get a volume less than what we would have got ideally, which was 50 ml. Tamam? Okay, so let's consider that the solution is not ideal and calculate it. Can we calculate this? Yes, we can calculate the total volume. We can calculate the expected total volume through using the partial molar properties, the partial molar volume. So we go to the thermodynamics textbook, okay, Smith and Van Ness. You'll find it there. Actually, this is from example 11.3, and let's get the partial molar properties of methanol and water when they form a mixture, and we want it when the composition is 30.75 mole percent methanol and the rest is water. So let's find it, and we have it here. This is the partial molar volume of methanol, and this is that of water. Now, how do we calculate the solution? Well, we use the summation of number of moles times the partial molar volume. Okay, so you multiply this by the number of moles here, tamam, and then you get, oops, sorry, pointing in the wrong direction. So you multiply this by this, and you multiply this by this, and then you sum it up. Tamam, you sum it up and you'll get this number, which is much closer to the experimental value than the value that we have obtained by just assuming an ideal solution. So basically what the partial molar volume means, it means this guy means what? That is the contribution of each species to the total volume, but of course the value is given per mole, so you have to multiply it by number of moles. Tamam. So the actual volume is not simply the contribution of the pure species volume. No, it's not. It's the contribution of the partial molar volumes to the total volume. Okay? And let me tell you one more thing. In fact, when we mix water and methanol at room temperature, you'll get the temperature of the mixture will be higher. Why is that? I'll explain in a bit why this is. Right, so we just explained why volume decreased after mixing. Now let me explain why the temperature increased after mixing. So let's look at the solution, that is after the mixing process, and let's look at the pure species, that is before mixing, and where we had pure methanol and pure water. And let me go back to volumes. Okay, so NS, number of moles of the solution, times the specific volume of the solution. Okay, compare it to the volume of methanol and volume of water, and tell me, plus volume of water, tell me which one is larger. Of course you would say the pure species volume was larger, right? Or the solution volume was smaller. Of course the above can be written this way: the total volume of the solution, you would say, was smaller than the summation of the volumes of pure methanol and pure water total. Okay, let me now compare the enthalpies. So compare the enthalpy, the total enthalpy of the solution at 25 degrees C to the summation of the enthalpies of pure methanol at 25 plus total enthalpy of pure water at 25. Which one do you think is bigger? Any idea? Well, the answer is that the enthalpy of the solution at 25 degrees C is less than the summation of the enthalpies of the pure species before mixing. Why is that? Well, as we said, when we form the solution, the volume is smaller, the bonding between molecules is more, so like new bonds are formed, energy released, the system is more comfortable. Okay, so basically we have the energy of the solution, the enthalpy of the solution at 25 degrees C is less than the enthalpy of the summation of the enthalpy of methanol and water before mixing. Tamam. So what does that mean? So that means you trying to fit all of this into this, but it will not fit because this is smaller, right? This is smaller. The capacity of the energy or of the enthalpy for the solution, 25 degrees C, is smaller than the capacity of the enthalpy of the methanol, pure methanol, and that of pure water at the same temperature. So what does happen? That means there is energy which will overflow, right? It will overflow. You're trying to fit this into this, but it does not fit. This is larger, so there is an energy overflow. There's an excess energy, right? And what happens to this energy? Will it vanish? Will it just destroy? Go away? No, it will not. It will try to escape to the environment, to the surrounding. Okay, but the problem is it doesn't have any enough surface area nor enough time to do at the beginning. So it stays inside the system and it will raise the temperature of the solution. So the temperature of the solution just after we mix the pure methanol and water together, the temperature of the solution will be higher, because the temperature will raise up to around 32 degrees C. And as I said, there is no heat transfer to the surrounding because there is no enough time, there is no enough surface area for heat transfer. Therefore, let me compare now. So that amount of energy stayed inside the solution, and it increased the kinetic energy of the molecules of the solution, which means the temperature went up. So now let me compare the enthalpy of the solution at 32 degrees C after being the temperature has raised, to the summation of the enthalpies of the pure species before mixing. So what do you think? Well, you're right, they are equal. Correct? They are equal because anything extra, which tried to go there, actually here I should say, anything extra, which did not fit here, that extra stayed inside. That extra stayed inside the solution, so it raised the temperature of the solution to 32 degrees Celsius. So now the heat capacity here, the amount of heat available here is the same as amount of heat available there. Okay, or if you like, you can write it this way. You can say, well, the summation of the enthalpies of the pure species at 25 would equal the enthalpy of the solution at 25 plus the excess enthalpy, So these two together equal these two together. Tamam. And if you take this into this, taban, it will raise its temperature, right? So it will go to 32 degrees C. So now this enthalpy of the solution equal to the enthalpy of the constituents, pure constituents, but at 25 degrees C. Okay, so some people call it excess enthalpy, some people call it delta H mixing. So the enthalpies after mixing, so the enthalpy of the solution after mixing, which is this, the enthalpy of this actually equals the enthalpy of the solution at 25 plus whatever excess or delta H mixing. So these two together equal these two together. Okay, so I hope now you understand why the volume decreased and temperature increased after mixing. Let me explain a little bit more so you feel more comfortable with the concept of ideal solution and ideal solution, and how we actually assume that we could calculate the energy or the enthalpy of a stream by summing up the enthalpies of the pure constituents.